and welcome to this Flexible Circuit Technologies webinar. My name is Matthew, and I will be your Global Spec moderator. And now, I would like to introduce today's presenters. With us today, we have Carrie Burkett, the Vice President for Flexible Circuit Technologies, and we also have Mark Finstad, the Director of Application Engineering, also coming to us from Flexible Circuit Technologies. To read more about our presenters, please look at the speaker bio window right next to the main presentation window. And guys, welcome to today's event. And with that, I will pass things along to you to get started.
All right, thank you, Matt, and hello to all. Thank you for attending. Prior to jumping into Mark's webinar, I'm just going to go through a couple quick slides here on FCT, more of an advertisement rather than a full presentation. And then we'll get right into the content that Mark has put together for today. Flexible Circuit Technologies, we're a global supplier of flexible circuits, rigid flex, flex heaters, membrane switches, plastic moldings, offering superior design services. Mark has put together a team of engineers where Mark offers 40 years experience. All of our senior application engineers offer 30 years and above. So we really do a great job helping customers get to cost-effective designs. And then from there, we perform value-added assembly, including SMT, product module builds, all the way to complete medical product box builds. From there, just a quick overview. Again, flex, whether single, double, multi-layer flex, rigid flex, flex heaters, HDI. We have in Shenzhen, where our assembly facility is, 9 full SMT lines, clean rooms, and do everything. Like I say, we ship bare flex circuits to customers, to assembled circuits, to product modules, all the way to complete box builds. From value-added services, localized support, again, the superior design consultation. We also, Mark is very active with IPCs, the Executive Vice Chair over all the IPC Flex Circuit committees. So we're very active with IPC, and he does a lot of education as well. We do prototyping, small to very large-scale production, component procurement and supply chain management, testing service, inventory stocking programs, and then put together account teams that take care of our customers. And then from a market standpoint, we focus on commercial markets, given we have Asia-based manufacturing. So for us, that includes medical, consumer, automotive, industrial, telecom, data being our main markets. We tend to grow at a rate of about 15% or more a year. So we've been growing rapidly as an organization. A lot of that has to do with the trends that are leading people to these solutions. The other thing about us, headquartered here in Minneapolis, Minnesota, so we kind of take care of all the front-end activities and commercial aspects with customers. And then our facilities in Asia are focused on quality systems and building great products and getting it out the door on time. The other thing is we have multiple facilities, and that really allows us to take care of customers, as mentioned before, small volume deals all the way to very large volume as well. Just pictures of our facilities. And then the other thing I would say, this is a great topic just because of the growth of these types of specialty interconnects. A lot of trends with miniaturization, OIT, or IoT, mobility, wearables, data collection, connectivity, all these types of things, challenging form factors, are leading developers and engineers to these types of solutions. So it's been growing rapidly. And yet what's challenging about it is there's a lot of people, jumping in, trying to offer these solutions, but it goes back to who's helping you with your design. Because, that's what matters. People that understand the materials, material properties, what can and can't be done, can really help you save time, but also can get to a more cost-effective solution that will perform for you. From there, just capabilities chart, which you can get off of our website. We also do flexible heaters, plastic moldings, a lot with the assembly side of it, which again is kind of a specialized skill. Many people are able to do assembly on rigid boards, but when you're talking about flex and unstable materials, having specialized skills, techniques, fixturing, and more really helps us be very proficient at the assembly side as well. And this just gives some added capabilities assembly-wise, going down to the 0105 components, smallest pitch, 0.25 millimeter BGA assembly, hot bar solder, ACF bonding. So we have a lot of capability in this area. All the way, as mentioned before, we do complete box builds as well. So that just gives you kind of a quick view, and there's a lot of information on our website. Our website is designed for the engineers that we often are serving, so you can get a lot of information out there. Our design guides out there as well. So certainly visit our website to find out more. So that's just a quick advertisement. With that, I'm going to turn this over to Mark. And as mentioned, Mark has 40 years in the industry as a vice chair for IPC Flex Circuit committees, a member of many of the other committees, also a columnist, and is just well known within the industry. So Mark, I'll turn it over to you.
Thank you. Here's the agenda for today. We've already gone through the introduction. We're going to start out with why to use Flex and some cost drivers, go through a mechanical layout module, and then go into bending and forming and what you have to know to be able to get a Flex circuit to conform to the requirements that you have. Flex circuits are being used pretty much in every niche of the electronic market that you can imagine, everything from aircraft and munitions to implantable pacemakers and defibrillators. And the main reason for using Flex is just that you're getting rid of wires. There's just not room in a lot of applications now to be able to hold all the wires. And a Flex circuit can give you much higher connectivity than you can get with just individual wires. I mean, if you look at a cross section of a bundle of wires, depending on the gauge of the wire, you may have actually more insulation in that cross-sectional area than you do actual conductor. Whereas with a Flex circuit or any PCB, you're stacking your conductors on individual planes and you can be much more efficient. Some of the advantages, we can make a much more streamlined form factor by getting rid of all the extra insulation surrounding every individual conductor that you have in a wire. We can make things that will fit much better in the application. You can also incorporate rigid PCBs, even though that's not the main purpose for using a Flex. Because they are all photo-defined and custom, we can many times incorporate rigid PCBs as part of the Flex and get rid of a lot of your connection methods. This is a big one. You can get rid of a ton of weight by getting rid of all that unused insulation that wires carry and the connectors that go with them. We can reduce the overall weight by 40 to 50% or more. That's pretty conservative. And you can also get them to take up a much smaller volume in your package. And for handhelds and wearable things, that's extremely important. Electrically, we're able to match differential pairs exact so that you don't have any problem with skew on them that you'd have on individual wires, because no matter how closely you think you've cut your wires and trimmed them, there's always going to be some inherent error there. And Flex circuits can, like I said, we can make the lines exactly the same length so you don't have that problem. If you look at the picture on the right, both of those go into the same application. And when you look at pretty much any electronic assembly, typically if there's a failure, it doesn't occur in the middle of a PCB or in the middle of a wire. It's usually where your terminations are. So by eliminating a lot of those terminations, you're going to increase the reliability of your PCB. These are just the classifications. We typically like to reference these if you are doing your drawing. You want to make sure that you reference IPC 6013. You probably don't want to be messing around with 50884 because that's pretty much obsolete now. It was the old spec that was used 20 or 30 years ago for the military, and we still see some legacy stuff there, but for the most part, that's inactive for any new designs. And so pretty much the entire world has moved to the IPC 6013, and 2223 is your design class or design specification that you want to reference also. We also have the material specifications. There are a lot of exotic materials that are coming on the market these days. If you're looking at using any of those materials, you will want to make sure that there is an IPC spec sheet that goes with it to ensure that the manufacturer of the material has gone through and done their due diligence to make sure that it has reliable and repeatable standards. So we're going to start with cost drivers. Flex circuits are many times compared to rigid PCBs, and that's really not a fair comparison because a flex circuit is always going to be more expensive than a comparable rigid PCB. If you look at the same size, shape, and layer count, a flex is always going to be more. Some of that is due to our material costs. Our flexible materials are considerably more expensive than rigid materials. But the biggest thing is that they're fragile and they're very, very hard to handle. And because of that, flex circuits just don't get the same kind of yield that rigid PCBs do. And because of that, the price ends up going higher. You're paying more for your material and shipping less off of each panel, and so that drives the price up. Flex circuits are always also very dimensionally unstable, which can throw a lot of loops when you're trying to stack up very, very tiny pads on internal layers, and then be able to drill a hole through them and make contact and get the registration that you need. And what's makes it even more interesting is that the materials can grow and shrink by 1 mil per inch just with temperature and humidity, and they don't grow and shrink in the same ratio in the X and Y axis. So trying to calculate what's going to happen can really can be interesting too. So that affects yields. So if you look at the heavy hitters, the things that have the biggest impact on circuit cost, it's very similar to what you'd see in a rigid PCB. The layer count, your circuit size, and your circuit shape and panel requirements. And those are the things that are going to have the single biggest impact, each of them. And when you start compounding, it can be even more. As an example, I first want to state that almost all flex circuits, while very, very high volume, million type piece or more orders are done roll to roll, the vast majority of flex circuits are done in panels. So if you were looking at a panel here, let's say just for argument, this is a 12 by 24 inch panel with a little bit of border on the outside for tooling holes. And you design your flex circuit and you need a certain length, you add a little bit extra service loop in there. And so when you send that to your manufacturer, he puts it on the panel and it turns out that it's just slightly over the halfway mark. No matter how you panelize that, the best you're going to be able to do is get 4 parts on a panel. Now, if it turns out that he put a little extra service loop in there that he didn't need and could get by a little bit less and was able to size it so it's just slightly less than half, he can now get 8 parts on a panel. So that extra 3/8 of an inch doubled the price of the circuit. So it can have a huge impact. So it's important to keep that in mind while you're designing and laying out your circuit. We'll go through a little bit of that in the mechanical layout module. But just keep in mind that the circuit size and shape has a huge impact on the cost of the circuit, because ultimately you're going to be buying that panel from the manufacturer. The less of that panel that goes in the scrap barrel, the less you're going to pay for the parts that come off. Here's just another example. If you had a rectangular part, and let's say you had just a single wire, a single connection needed to come off, if you incorporated that single connection into the, down here, you've reduced your panel density by 25%. So that single wire increased your cost of your circuits by 25%. It's almost a straight linear function there. So in this particular case, maybe it is a good idea to just add one single wire. And that's something that you would have to make a decision as an end user on whether it's worth the extra cost to put that wire on or whether you just want to have it incorporated into the flex. But keep in mind that it does have an impact on the cost. This is one that drives a lot of manufacturers crazy when you get a part that you're building, and with the data package, they also send you the requirements for the way they want the part shipped to them. And if they're going to be doing the assembly, they'll send you a panel layout and the layout of the parts on the panel. Now, if you look at this particular one here, this is really not a great use of space. About 2/3 of this material is going to be thrown in the garbage as scrap. You look at how far the parts are spaced apart. If that was repalletized, you can get 3 times as many parts on a panel, but only increase your material costs by about 50%. And so you have a slight increase in material cost, no increase in processing costs, but you're getting 3 times amount of parts going through that get shipped out on that material. So that can have a huge impact. And it's a good idea to discuss that with the manufacturer before you make these requirements, to make sure that you're not adding a lot of costs that doesn't give you any value. Another thing that has a huge impact is unreasonable X-out requirements. And I'm going to go back to the previous slide to illustrate that. Let's say that we got this as our layout, and while it's a good layout, if there was a note on there that said we don't allow any X-outs, that means that if I build this particular panel and I end up with one part that's a reject, I have to throw that entire panel away. And I can tell you that there's no manufacturer that is willing to just eat that. What ends up happening is the cost of all those 11 good circuits that were on that panel that are going in the garbage now will be amortized into the parts that do get shipped. And so that'll have a huge impact on cost. And it's really not I don't really understand why we get these requirements a lot of times, because pretty much all modern pick and place equipment will automatically ignore rejects on a panel. And I can understand not wanting 90% of the panel bad, but having only one X out probably certainly isn't a reasonable requirement. So just keep in mind that will have an impact on the cost.
We do have a couple questions that not so much on cost drivers, but here's one that came in. By ultra thin materials, what thickness are we talking?
Ultra thin, you're typically talking, our standard materials are 25 micron for dielectrics and adhesives, and copper weights were going down to 12 micron as kind of the minimum standard, which is 1/3 ounce copper. So that's kind of what we're seeing on that for materials.
And we had another one that had to do with the EV cell pack applications where the FPCs can be very long. What is your maximum length? And I know, for us, we've been doing circuits up to a meter, meter and a half. We actually have now requirements for up to 2 meters, but that gets into, it depends, it's design dependent and volume dependent, because as Mark mentioned, you get into these longer circuits, you almost have to go to a roll-to-roll process. And so that's going to be design dependent as well.
Yep. Another thing that impacts the cost is the circuit type. Whether you're going with a rigid flex versus a multi-layer. And here's an example. Multi-layer is just multi-layers of pure flexible material that's drilled and plated through. Rigid flex actually adds rigid cap layers, and adding those rigid cap layers, it ends up increasing the complexity and the amount of processing time, so it can have a pretty good significant impact on the cost. And so if there's a way you can incorporate a multi-layer versus a rigid flex, that can save you some money also. Typically what I use as an indicator on whether you need a rigid flex versus a multi-layer is whether you have SMT components on one or both sides. If all your SMT components are on one side, you're better off with a multi-layer, because we can put a rigidized stiffener on one side and give you a nice, stable, flat, rigid surface to mount to. And if you have them on both sides, you typically are going to be driven to a rigid flex. So this is a rigid flex here. You can see that it has the SMT and they're on both sides. This is an example of a similar type circuit that's just a rigidized flex. And here's the back side and the front side. So you can see we put the rigidized backer on, and so you have a nice rigid surface that you can mount to, and you can save yourself a lot of money by doing that. We're certainly capable of doing either version. It's just that I don't like people spending money if it's not getting them value. And when I say all the components have to be on the same side, that's in each rigidized area. So if on the other end of the circuit you had rigidized, or you had components on the other side, that's still fine, as long as each area that has SMT is all kept on one side of each of those areas. You're fine. You can go with just a standard flex with a stiffener. Feature size, obviously, as things get smaller, the odds of having strand flaws increase. And so whether it's pads, traces, or spaces, bigger is typically better. There's kind of industry standards that, when we start getting down in trace and space, while everyone can go down to, 25 microns or less, no one's really doing it without it having a pretty good impact on your yield. So typically 75 micron trace and space is that stepping point where you start really having an impact on yields. And here's just an example. Let's say you have a 4-layer circuit. And so you have one pad, and now you have to take your next layer and stack it up. You have a little bit of misregistration. You do your next layer, and it's off a little bit, and your next layer. And now you have to try and drill a hole and make sure you hit all of those pads so you have annular ring on each layer. The fact that the materials are moving around, they're dimensionally unstable, can really cause a problem. And even though we have smart drills that will help us align that hole to better center it, if we have to do this with sequential laminations and LDIs or using expensive targeting for our drills, typically the stuff that's processed on those pieces of equipment is going to have a cost adder also. Your material types can have an impact on it. The standard is an adhesive base where your copper is laminated to your dielectrics, and that's the way we purchase our materials. The copper is already on the dielectric, and it could come either with an adhesive bonding it or adhesiveless where the dielectric has been cast onto the copper. There's some others like LCP and some other non-standard exotic materials, and typically there's going to be a cost adder when you go to things that are not as mainstream. Polyimide is kind of what rules the roost as far as dielectrics, and either epoxy or acrylic thermosetting adhesives are what hold everything together. And unfortunately, a lot of the current materials that have been around for decades, while they have a lot of really good properties from a high-speed design standpoint, they're not so good. There are some new materials that are on the market, and all the main manufacturers have their own version of it, but they're thermal setting adhesives that have performance very similar to LCP as far as their loss tangents and dielectric constants. So there are some things out there, but they do come at a cost. As far as via types, we could spend an hour going through that, but just as quickly, keep in mind that every unique via structure that you have in your board will have a cost associated with it. So if you have through holes, that's one via structure. If you have a blind via coming from 1 to 2, that's a second via structure. If you have blind vias from your bottom layer up 1, that's a third. Buried vias inside are unique. Even if you have 3 buried vias, but they're not in the same layers, they're each a unique via structure, and each of those will have a cost associated with it. So anything you can do to try and eliminate as many unique types of via structures you can will help you with the cost of your flex. Over dimension drawings, it's important to keep in mind that flex circuits are flexible. You can't dimension them like a piece of machined steel. And there's been times in the past, I had one situation years ago where I had a fairly long circuit and didn't realize until it was in production that there was one dimension on this 2-foot long circuit. They wanted a plus or minus 0.10 of an inch on the overall length. And we built the parts, and they all passed our inspection, and we sent them to the customer. And I got a call about 2 weeks later, and the customer said, "Your parts are all too long." So I had them send them back, and when they got back, I measured them, and all the parts were in. And so I sent them back to the customer, and they called me a week later and said, "Why'd you send them back to us? They're too long." And I said, "Well, I measured them; they were all good." And this happened, and they went back and forth several times, and I was starting to be I was a little concerned that maybe their measuring equipment was off. But then I realized what was happening is that this was happening in Minnesota in January when it was 20 below zero out and humidity is 2%. And we were sending them to Tampa, Florida, where they sat on a shelf for a few days before they were processed. And they were literally growing and shrinking by about 15 thousandths of an inch just in transit. So last time the guy called, I said, throw them in an oven for 15 minutes at 250 degrees and remeasure them, and they shrunk right into tolerance. But I guess the long and short of that story is there's no reason there should be a tolerance like that on a flexible circuit. It is a flexible circuit. By all means, if you have a critical dimension, put it on your drawing. If it's not critical, don't put it on, because if it's on the drawing, we have to verify it, and that will have a cost associated with it. Dissimilar layer counts. This is typically on rigid flex or multi-layers. I do have customers that will sometimes say I need a rigid flex, and it's 8 layers, and I have 3 individual hardboard areas, but I only need 8 layers in one of those hardboard areas. Can I save some money if I only put 6 layers in the other areas? And I said, well, it's going to change the cost, but not the direction you want it to go. You want to have every area that is rigidized to have the same number of layers. We can eliminate flex layers that are jump between them without a lot of fanfare. But in the actual rigid areas, because of the way rigid flex are processed, you want to make sure that even if you don't have circuitry on those extra layers, just put pads in. But you want to have the same exact layer count and stack up in each of those rigid areas. Excessive size, over 18 inches. That's where you typically start seeing it bumping up. A lot of that is due to limitations of the processing equipment. A lot of the processing equipment can do long lengths, and others are not made for that. Printing machines, for instance, are typically, your printing frames are limited to about 2 to 3 feet in width and a couple feet in length. And so that can limit you. There are some ways that you can work around some of that stuff, but anytime you start getting a longer circuits, expect that there is going to be a cost adder, and that usually kicks in around between 18 and 24 inches, where you start seeing an increase in the cost.
Which actually leads to, I have a question here. What is the longest flex length you are capable of fabricating? And that's interesting because we have really long.
Yeah, and a lot of that depends on the feature sizes. If you had 5 mil lines and spaces, we're not going to be able to go very long, just because to make something that was 20 feet long and not have a single strand flaw anywhere in 20 feet would be very difficult. If you have very wide lines and spaces and you're using maybe 1 ounce copper, so a little bit more durable copper, and you're okay having some seams in your covers, because that's another limiting factor. Is the other limiting factor is your lamination presses. Most of those don't go over about 3 feet in any dimension. So we typically have to put seams in the cover. But if you don't have any plate through holes, we can probably go 8 or 9 feet. But like I said, there will be a cost associated with that, and there'll have to be some. There's a number of caveats that we would have. Another thing would be plating. We wouldn't be able to have plated through holes. It'd have to be limited to a single-sided circuit. So there's a lot of what ifs that you have to go through to determine what the actual maximum length is that you can do.
Splice applications.
Yeah, no, and we do splice. We splice circuits together using hot bar solder or anisotropic adhesives, and we can make long lengths, but they're built in smaller sections. So you have another question here. In dimensioning, what geometric tolerances do you recommend? In other words, what % growth might you expect due to humidity or other factors? Typically, it's 1 mil per inch we see due to temperature and humidity. That's pretty standard. So if you have a 20-inch circuit and you put plus or minus 10 on it, the materials won't even support that, much less the processing. There's other things like as you remove copper from our pre-clad laminates, the laminates will shrink. So you may lose some of that up front, and then if you get humidity, it may grow back into tolerance. So lots of things can happen, and we're pretty good at predicting and what's going to happen after all these different processes. But like I said earlier, if you have a critical dimension, put it on the drawing. If it's not critical, remember it's flexible, and just let the circuit be flexible and take up that dimension.
I have one more that asked if we have manufacturing footprint in Europe for local content. We do have representation in Europe. We do not have a manufacturing location at this time. That's stated. We have some very large, significant opportunities we're working on in Europe where we're evaluating. That would be out a ways. And likely, if we do put a location in Europe, it would be more assembly. So we'd still build the flex in our Asia-based locations. So that's something under consideration.
Okay, if we're get back to the cost drivers, copper weights. What we're seeing is the industry is moving to thinner. Like I said, 1 ounce is about as thick as you see these days. It's rare that you see 2 ounce copper. Typically, people need 2 ounce copper. We'll plate up 1 ounce copper, put an extra ounce of copper on top of it, and get the 2 ounce that way, because we're not seeing a lot of need for that. 1 ounce, or 20 years ago, 30 years ago, was kind of the leader. That was replaced by half ounce, and now we're seeing 1/3 ounce as being kind of the most used, followed by half ounce, and then 1 ounce is kind of a distant third. Multiple final finishes. Here you want to pick one and go with it. You can use multiple final finishes, with solder and eating or something like that, but unfortunately, there's no way to automate that. That's a hand process that's done where, in order to do it, we have to mask off one area of every circuit by hand, put on the first finish, strip off the mask, remask the area that we just plated, put on the new finish, then pull off the mask. And so there's just a lot of touching that goes on, and that's going to have a big increase on the cost. So the best thing is to find a final finish that works across the entire circuit. Anapeg is becoming very popular, and so I recommend that as maybe a potential switch to Enig if that doesn't meet your needs. So that's it for the cost drivers. Now we're going to be doing the mechanical layout. A lot of people are kind of get the deer in the headlights look when they have to lay out a flex. Biggest thing to keep in mind is that on virtually every flex, there's multiple ways that you can do it. So I've just kind of the steps I go through is I look at the termination method. Hopefully that's already defined that you want for each area that this thing is going to connect. A lot of times that's left until the very end, and the flex circuit has to make up for all of the downfalls of everything else in the system. But if you know what the termination is, note that. There's lots of things you can use. Pretty much anything you can put on a rigid PCB, you can put on a flex, whether it's mating connectors. ZIF connectors are kind of unique to flex, and it's a great way of terminating them. You can't do that on a rigid board, but you can do it on flex or FFCs. Unsupported fingers is, again, another thing that we can do on flex, but you can't do on rigid. Card edge connectors, don't see a lot of that anymore, but they are still occasional. And then pins or other connection hardware. One thing you want to look at on your connectors is whether it's offered in both straight and right angle, because there's times where you may be able to eliminate a bend in your flex by just using a right angle connector and making the turn that way. So that might save you a little bit of length on your flex and eliminate one potential reliability concern. So you want to next identify the usable space in your enclosure. And this is just a 3D printed dummy that I put together for illustration purposes. And you can see that there's a round circular connector here. There's some straight connectors here and a card edge connector over here. And I need to connect all of those together. Just another view. So you want to identify what your requirements are. Do you need service loops anywhere that you for the assembly process? Do you need, do you have room for bend radii to get, you're not going to be overstressing your flex. And then also, consider your assembly process. Someone's going to have to put it all together. So something that may look really pretty in SolidWorks may not be the easiest for an assembler to get into that position. So take that into account also. So the first thing I do is generate a rough outline in CAD or on paper, and just to get a kind of an overview on how it looks. I prefer to do it in CAD so that I can kind of keep track of what changes I make, and if something that I do gets worse, I can always go back one iteration and not lose anything. And as I recommended, there's always multiple ways you can make connections, so always keep that in mind if things aren't fitting. So you generate your paper doll, print it on 1:1 scale, and do a fit check. So here's my layout that I came up with for this particular application. And I put in some dash lines where my fold marks were going to be. You can also put in cardboard stiffeners if you want to rigidize an area that you may have a mechanical stiffener in the final product. And so this was my paper doll. And so I formed it the way I wanted to go in. And I was actually very pleased. And this was just the first shot through, and normally it doesn't fit that well, but I was pretty happy that it looked as good as it did. So I moved on. The first thing you do is you evaluate the size and shape that you did, and was it easy to assemble? Did you tear the paper when you tried to put it in? If you tore the paper, that may indicate that there's going to be some stress put on a flex when you try to do it. So if there's an issue there, you might want to look at ways to either strengthen it or reroute the way way the flex gets from point A to point B, so you don't have that stress concentration point. Again, going back to the cost drivers, will the circuit fit efficiently on a manufacturing panel? If you are taking up a huge amount of space, there may be another way to get the same thing done that's more efficient and will bring the cost down. So you make any changes that you need to do and then repeat the steps, make another paper doll again. Since my first one had worked so well, I moved on to this step, which was to generate a Mylar mock-up. And just getting yourself a sheet of polyester will be a pretty good simulation for a flexible circuit. It may be a little bit stiffer, but you can print that on a printer and cut it out and do a fit check and then modify it as needed. So it doesn't show up real well, but that polyester mock-up is actually in there, and you can kind of see it a little bit in this area here, and it's there, and everything seemed to fit pretty much the same as the paper doll did. So I was happy with that. So the next step, and this is something that is definitely worth the time and effort and revenue to do it, is to generate an actual mechanical sample with the actual materials that are used. And this sample would basically just be all of the materials with no photo-defined features at all. Basically everything stacked together, laminated, and machined out. You can put in tooling holes, you can include stiffeners, nothing that's going to be, like I said, there's not going to be any kind of photo-defined feature, so it's only for mechanical fit and form. So this is the mechanical mock-up I made. As you can see, there's nothing other than just solid copper, and there are stiffeners in the 3 areas they wanted rigidized. And I formed that, and it wasn't until I got to this point that I realized that there was an issue, and I hadn't seen it on the previous samples, and that's right here. There's actually a little bit of a clearance interference on that spot, which doesn't seem like much, but when you try to force this area in, pushing this in this direction, you end up with a buckle, and this would pucker out. And if you needed to put the cover on, this would be forced against the cover. There's a good chance there could be some abrasion concerns there. If I hadn't made this mechanical sample, I would not have noticed that there was this problem right in this area. So this was what really brought that to light. And over the years, I've had many customers that have called me after they've done a mechanical sample and said, oh, that mechanical sample saved my butt, because I would have had 10,000 of these things sitting on our dock and none of them would have fit if I hadn't done that mechanical sample and made a tweak prior to ordering the large quantity. So after you've done that, you look for any miscellaneous concerns, abrasion, are you making contact? Is the flex rubbing against something that could vibrate through at some point? Is it up against a component, a sharp pin, or anything like that? If there is, you're going to want to try to modify the shape. There's things you can do to protect it. Teflon patches will keep it from tearing. Stiffeners will keep you from having holes punched through it in certain areas. And when it's all installed, the flex should be in a relaxed state. If the flex is like a banjo string, that's going to cause problems. So it should be in a nice, relaxed state where there aren't any residual stresses anywhere. And you may want to add strain relief or stiffeners or other anchoring hardware to hold everything in place. So we'll move on to the next one, which is bending and forming. And there's kind of a misconception for people that aren't in the flex industry that if you make a flex or a circuit, a PCB out of flexible materials, that you can bend and form and do whatever you want with it. And that's not really the case. A well-designed flex, you can get millions of cycles out of it, and a poorly designed flex will fail very, prematurely. So it's important to understand what happens when you are bending a flex circuit. So let's take a very simple example here. So let's say this is a single layer flex. This is a cross-sectional view where you have a single layer of copper in the middle, polyimide top and bottom covers with thermosetting adhesive holding it all together. When you bend that 90 degrees, you're going to have compression forces that form on the inside of that bend and tension force that forms on the outside of the bend. And this happens on any material that you bend, whether it's a flex circuit or a 1/4 inch plate of steel. You're going to see these same forces. And somewhere in the middle of this stack, you're going to have an area that we call the neutral bend axis. And the neutral bend axis is defined as a planar region in the center of the stack that has 0 thickness, because it's an imaginary line or imaginary plane. And that plane does not experience any tension or compression forces. So the key is to figure out where that neutral bend axis falls, because it's not always dead center. A lot of things can affect it. If you have heavy copper conductors or copper planes, because they are very rigid, they'll resist stretching and compressing, and the neutral bend axis will tend to be drawn towards those layers of materials in your stack. If you have thick polyimide layers, anything over 3 mils in thickness, those are also going to be very stiff and robust and are going to resist stretching and compressing, and so that will tend to drag the neutral bend axis into those areas also. If you have combinations of those materials, they tend to cancel each other out. So you may want to look at that. You don't want to have, a couple of heavy copper layers and a couple of layers of thick polyimide, all almost like a lopsided construction where they're all stacked on either the top or the bottom of your circuit, and then try and bend it, because you're really going to amplify those compression and tension forces. We typically like to see a balanced construction whenever possible. That just keeps that neutral bend axis fairly close to the center of the stack to equalize the forces between the inner and the outer portion of that bend. Bend angle can have an impact also. I can tell you that if you bend something at 45 degrees, it's almost impossible to damage a flex circuit regardless of what your bend radius is. You're just not bending it far enough. It's usually around 90 degrees that we start seeing issues with bending if you have a stack up that doesn't support the bend, and at 180 it can become even more pronounced. Your bend radius is very important. Here we got 3 circuits that are exactly the same. All of them have the same bend angle, but I can tell you that this one here is going to have a much better chance of failing than this one here, just because the stresses are focused in a much tighter area than they are on the other one. And if you take one thing away from the seminar today, this would be it. This is the bend ratio, and I can tell you that anybody who designs flex circuits uses this every single day. I've been using it every day for over 40 years. This is a ratio of the bend radius to the circuit thickness. And this will basically give you a pretty good idea if you're going into an area where you should be safe, or if you're into an area that could really cause some problems. The IPC has recommendations, and for a single-sided circuit or double-sided circuit, it's 10-to-1, so 10 times the circuit thickness for your minimum bend radius. For multi-layers, it's 20-to-1. For dynamic applications, I have 100-to-1 for a dynamic, and that's the minimum. I'd like to see double that. I can tell you that the static applications, they are violated all the time, and they can be violated safely all the time. But that's a good idea to, when you have something like that, let's say you come in and you're at 8-to-1 or 7-to-1, you don't have to throw everything in the garbage. that's when you pick up the phone and give us a call and say, am I safe here? And there may be some things that we can help steer you to get a design that will be able to support that tighter bend radius. It may be tooling, it may be handling, it may be just the layout of the circuit. But after doing this for as long as we've been doing it, we've seen a lot of things that work and a lot of things that don't work, and can probably save you a lot of headaches. Here's what happens when you have excessive tension forces. You can see you have a heavy layer of copper and a heavy layer of polyimide in this area here. Because of that, your neutral bend axis was skewed in, and that ended up causing excessive tension on the outside. And what happened was right here, the polyimide cover cracked, and because of the bond we have between the polyimide cover and the copper, it took the copper with it. This is everyone's worst nightmare. This is a 4-layer circuit, and I can tell you that this is way overformed. It's about a 1-to-1 bend ratio, and I would not recommend this really for anything at 90 degrees. You're gonna have a problem. What happened here, you can see that on these outer layers, the copper thickness is actually stretched. You can see that it's, you look at the difference in thickness. So there's been so much tension out here that you've stretched that outer layer, and right here, there's a hairline crack. And it looks like it's still electrically connected, so there's a chance that you would be able to install this and not realize it was a problem. But if this is going into any kind of application that's going to see any shock or vibration, a couple of bumps on the road, and that may open up, and that's an expensive time to find a strand flaw. This is what happens when you have excessive compression forces. Here you can see that we have heavy copper and a thick layer of polyimide, and so we end up with this rippling in this area. And this by itself isn't a problem. You can see that where the adhesive is, you have a full bond there, there's no laminate voids, and so this by itself is not rejectable. If I was seeing delamination occurring in the area where you're seeing that puckering, that would be a problem. But if everything holds up, this is fine. So a few design guidelines. If you have small, fragile conductors, you start getting down under about 0.06 of an inch in trace width. I like to keep those on the inside the neutral bend axis because that will put them in slight compression. And I found that those conductors seem to tolerate compression a lot better than they tolerate tension. If you have a single plane layer and you can keep that close to the center of your stack, as we talked about earlier, that will tend to draw that neutral bend axis into that area and keep your neutral bend axis hopefully reasonably centered so you can equalize the forces between the inner and outer layers. And determine and evaluate your bend ratio. Again, this is so important. Again, it's not it doesn't mean that that you can't move forward with your design if you're not conforming exactly to what we have there. Those were set up to be intentionally conservative. But if you do your calculations, you're at 15-to-1, you can probably move forward without a care in the world, and you'll be fine. But if you drop below that, it just means you need to start using some caution and giving us a call and making sure that you're not going to have a problem when you put it in the application. Another way to increase flexibility is to utilize unbonded areas, and by that I mean this is a 7-layer rigid flex cross section. And there's 7 layers in the rigid area and 5 layers in the flex area. And the customer was having a problem with this because it was just too stiff and they weren't able to get it in. And so we recommended going with an unbonded construction. And what we do is we unbond only the flex areas. So the individual layers can be unbonded. That can be any combination. And what we did is we did a 2-layer, a 1-layer, and a 2-layer. And that made it a lot more flexible. And the customer really liked it. And they said, well, that worked out well, but what if we did it as 6 or 5 individual flex layers? And that can have a definite impact on the cost, and didn't really seem like I was going to buy them anything, but they were pretty adamant that we go down that path. So we did make some samples, and this was the result. And unfortunately, because of the way circuits behave when they're unbonded, we ended up with a secondary reduced bend radius right here, and this was actually bent over 180 degrees when it was installed. So this got even more pronounced than it's shown in this picture here, and they actually got stress cracks in that area. So in this particular application, being just a little bit stiffer was acceptable, and that's where they probably should have stayed. Going with more flexible actually caused more problems. So there is a balancing act there. And again, that's one of those things that we learn as a manufacturer, and so it's a good idea to give us a call so you can lean on our experience. You want to keep plate through holes away from bend areas. It's hard to calculate what happens between the layers with those tension and compression forces, but anytime you have a structure that bridges between them, it can be very problematic. This is a bend that I did right on a via, just to show that if you bend it tightly enough, you can actually distort the via. And in this particular case, it doesn't look like the via failed, but I wouldn't want to put that in any kind of life-saving equipment, that's for sure. You want to make sure, whenever possible, your conductors pass through your bend areas at 90 degrees. And by that, I mean, if you look over on the left side, you can see that all the traces are going through perpendicular, but over here, they're going through at an angle. And this isn't a problem by itself if it's a static application. If it was going to be high vibration or semi-dynamic, it might be more of an issue. But if you can go through perpendicular to the bend, that's the way you want to go. This is the I-beam effect. By stacking conductors on multiple layers, you're essentially increasing the thickness, and the thicker your board is, the more tension and compression you're going to create when you form it. So we typically recommend staggering those traces like you see in the bottom there. And a lot of designers like to have their signal return paths stacked on top of each other, and that's fine, but then stagger the pairs. So you'll end up with these here would all be shifted in between, so they fell in the middle there. And that way you can kind of, again, the balancing act. You'll make it slightly thicker, but not so thick that you end up with mechanical problems when you bend it. And this is the second thing that you should come away with today, if other than the bend ratio. This is ultra important. Ensure that there's no discontinuities in your bend area, anything at all. No cover openings, no plate finishers, no changes in conductor width, directions. Nothing should change in the actual bend area, or even radiating out from that bend area, at least one radius width on either side, because those radiuses those forces can radiate out. Over the 40 plus years that I've been doing this, I've seen lots of flex circuits fail, and on every single one of them, I've been able to narrow it down to something that concentrated the stress in a particular area. So just make sure that you have a uniform construction and there's no change or anything that can cause a stress concentration feature on your flex circuit.
I do have a question that came in. What are recommended strain relief for pad to wire interconnects? Example, it says UV encapsulating fluid. Yeah, for encapsulants,
there's a lot of things you can use. What we personally use is a product called 3M2216. It's a very durable epoxy. It never gets, it gets very hard, but not brittle hard. You can still dent it a little bit with your fingernail, but it bonds very well to all flex circuit materials. And if you have that over your solder joint, you will not pull the wires out. You'll pull the entire patch off before you would get those the capsule to fail. So here's an example of a stress concentration feature. In this particular case, there was a customer, we were working with two different groups that went into a guided munition, and these modules would plug together. And the one group was engaged with us on a regular basis. The other group was really pretty distant. And they asked for these, what you're seeing here is a silver epoxy shield on the outer layers. And then they wanted these vias that went down to connect that silver epoxy to the layers down below. And I requested that they remove those any place that they were bending them, and they told me it was an electrically noisy environment and they needed to have those vias. And I tried to explain that because flex circuit materials are so thin, there's really nothing. If your 3 dielectric thickness is inboard, you're not going to have any problem with noise. But that's the way they wanted to go. And so we got a call, and they said that you need to come down here because your circuits are breaking. And so I showed up there on Monday morning, and they had one of these circuits that was in a couple of pieces laying on the desk. And I said, well, how are you forming them? And they said, well, we don't really know. The operators do that. And that's a problem. If you don't have a solid, repeatable method for forming them, that's a recipe for disaster. So anyway, we went out into the production area, and it turned out that, one guy was forming around the edge of his desk, and one guy was using a ruler, and someone on night shift was doing something else, and no one knew what that was. So that was an issue. What was happening is because these vias were there, they caused a stress concentration point. And after just a single bend, as they were trying to get this thing packed into where it needed to go, they were getting these creases that then propagated into cracks and ended up going all the way through the circuit. And by the time they were able to extract it, they had torn it completely in half. It turned out that we were allowed to remove the vias in those areas where they were bending, and we also made them a forming tool, and that solved the problem for them. So again, it was important to, if they'd had that engagement earlier on, they could have saved themselves a lot of headache, because the other group whose circuit plugged into this one had no issues whatsoever. Here's another place where you can have a stress concentration feature. If you were to bend it along this line right here, you can tell that this area here, because of the copper, is going to be very rigid. This area going this direction has the solder mask, and so these little conductors right here are going to be bearing the brunt of all of the stretch and compressing, and you're probably going to get cracks that are going to form in these areas.
I don't think we're going to have time for the forming section. I don't know how many slides you have.
Oh, we'll go quick.
Okay.
So we're going to go quick through here. There's 2 ways to form circuit, heat forming and cold forming. We typically like cold forming. It's a less expensive process, and it's less damaging to the flex circuit. When I say cold forming, though, typically you don't want to do it like this or like this. Here's one application. It's very simple. It's just an arbor press with some high durometer rubber and a known radius on the edge of the forming tool. You force that into the rubber, and you can get a repeatable form each time. This is another one. This is a little bit more elaborate, but this is just a 3D printed jaws that I put on a standard parallel gap pliers. Just take into account the radius and the thickness of the circuit. When you design these, you also have to overform slightly, and you can put it in and squeeze it, and when you're done, you end up with the same form every time. It doesn't matter if it's an 80-pound woman or a 300-pound gorilla doing the work. Everyone gets the same results. This is a little bit more elaborate one. We needed 2 bends that were had to be exactly spaced apart a certain amount. And so this was basically just a piece of machined FR4. It could also be a 3D printed block that was put into that same arbor press with a mating cavity, and it was forced down. And we had actually added copper to the outside just to give it a little bit more memory. So when we formed it, it wouldn't relax at all. This is a twisting application. I wouldn't recommend this if it's not necessary, but it can be done. It required a much more elaborate tool to make sure that the twisting was isolated to a very small area. You can see this is the area where the twist was occurring, and if that occurred over a smaller area, it would have torn the circuit, and that's what we ended up with. Heat forming. Keep in mind, if you're going to heat form, circuits get very fragile when they get hot. Don't ever use a heat gun because it's not controllable. 1 inch away from the nozzle, it's 900 degrees. If you're a foot away, it's only 150 degrees. So it's not really something that's good to have on the floor. You always want to cold form your circuit first, then heat it to temp in a fixture. Allow it to cool at room temperature, still constrained within that that forming tool, and then remove it from the tool. And when people ask what temperature you form at, the best temperature is the lowest one that works. And I would literally start at about 150 degrees Fahrenheit and then go up from there. If you get up to 275 and it's not holding the form you want, there's no reason to go any higher, because at that point you've softened it about as much as you're ever going to. So that's kind of your range, is between 150 and 275 F, but the lowest one you can use that works is your best bet. So this is an application here. It's an application here where a customer did try to use a heat gun to form one of our circuits, and the picture doesn't really do it justice. It's much uglier than it looks. These areas here are actually completely delaminated and blown apart. And what had happened was they had heated this thing with a heat gun because it was too stiff, and that made it soft and easy to handle. And when they bent it, because of the tension and compression forces, it blew the bonds inside there. So there are actually traces just dangling inside there, and they ended up shorting. And so they had roughly $250,000 worth of product that they destroyed because no one noticed that this was a problem, and they were all put into this military chemical weapons detector, and they all ended up having to be extracted and replaced with new parts. And this is what it looked like after we incorporated a $2,500 forming tool that could have saved a $250,000 mistake. And again, this is one where they should have engaged and listened to the advice, because again, with the number of applications we've seen, we pretty much know what's going to work and what's not going to work.
All right.
And that's all we have. So we'll turn it back to Matt.
All right, thanks guys. Thanks for that great presentation. Also, thanks for answering some questions from our audience throughout. We appreciate that. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.